Right now, beams of starlight are vanishing into invisible maws. Yes, light really can fall, and black holes eat it. Anything that crosses the event horizon is gone for us. You will hear why that includes more than rocks and gas. It includes photons and even ripples of space itself. The basic picture is simple, and the details are wild. A black hole is gravity turned up to an extreme. Space and time bend so hard that all paths aim inward. Cross the boundary and every future step points deeper inside. That is the immediate takeaway you can hold on to now. Bottom line, once past the horizon, nothing can signal back out. You drift toward a dark sphere, ringed with molten light. That glowing ring looks like fire, but it is gas. The boundary ahead has a precise name, the event horizon. It is the point of no return for light and time. Care about it because it decides what can ever reach you. Beyond it, signals cannot climb back, no matter how clever. Gravity there is geometry, not a pull from a hidden hand. Paths through spacetime bend, and every future direction points inward. Even a laser pointed out becomes trapped by that geometry. From far away, falling things slow and fade to red. Their clocks tick slower, their light stretches, and then it vanishes. Up close, the crossing is quick and frankly uneventful. You would not see a wall or a special shimmer. Your future simply leads inward, the way down a waterfall. Quick reality check, the horizon is not a solid surface. Nothing scrapes there unless tidal forces are already catastrophic. Around supermassive holes, those tides are mild right at entry. So the picture is simple. The horizon is a one-way door. Shift your gaze to everything swirling around that ring of fire. Dust, gas, asteroids, and whole stars are obvious candidates here. But photons fall, neutrinos fall, and dark matter falls too. If it carries energy or momentum, the whole can take it. Care, because that rule includes things that feel intangible or weightless. The path in is written by spacetime, not everyday push and pull. Massive stuff follows time-like paths, leaning inward as gravity deepens. Massless stuff rides null paths, which tilt inward near the edge. Inside the horizon, every path points forward and inward together. Radiation pressure cannot save you once that tilt exceeds straight up. Magnetic fields do not form shields. Fields themselves are bookkeepers. They track currents in plasma, which the whole gladly consumes. Neutrinos barely interact, yet they still obey spacetime's tilted roads. A beam of gamma rays can add mass and spin. A cloud of dark matter can fall silently and hide. Example, in real terms, the whole grows even when fed light. M87's core swallows starlight by the trillions, day after day. Net result, if energy crosses the horizon, the black hole keeps it. Now cut the noise and ask what the hole remembers. In plain words, almost nothing about the meal survives outside. Physicists call this the no-hair idea, with 3 exceptions. The exceptions are mass, spin, and electric charge, measurable from afar. You should care because erasure is the ultimate cosmic blender. Lose the details, keep the totals, and the outside story simplifies. Mass adds when anything energetic falls, including light and neutrinos. Spin adds when infalling stuff has swirl aligned with the whole. Charge adds if more positives than negatives fall across the edge. In practice, surrounding plasma cancels charge quickly, keeping holes essentially neutral. The messy shape details get radiated away as gravity waves. The curved horizon relaxes, and the hole rings like a bell. After that, ringed on the exterior matches a simple rotating solution. That solution is a Kerr black hole, or Kerr Newman if charged. Example you can picture, M87's silhouette hints at a rapid spin. Its jet aligns with a rotating engine, tapping that angular momentum. One sentence recap, outside you only read mass, spin, and charge. There is a mind-flipping way to picture what actually falls. Think of space as a river, streaming inward toward the center. The horizon is where that river matches light speed flowing in. This matters because it explains why light cannot swim back out. Outside, the inward flow is slower than light, so escape is possible. Inside, the flow outruns any outward effort, even a laser. Nothing locally breaks light speed, the river itself simply carries you. Geodesics are just the straightest lines in this moving medium. Tilt increases near the edge, turning every forward step more inward. Fire a rocket outward and you only slow the plunge. Fire a brighter flashlight and the beam still drifts downstream. Cross the boundary and downstream means deeper space, not later time. Example with numbers, a supermassive horizon might be millions of kilometers wide. You could cross it in seconds without drama or ripping. A stellar mass horizon is tiny and far more violent. Bottom line, picture a current of space, and you grasp inevitability. Now we face the scene everyone dreads, the stretching and tearing. Tidal gravity is the force difference between your head and feet. It matters because it decides whether crossing feels gentle or lethal. The gradient grows when the black hole mass is small. Near small holes, your feet fall faster than your head. That difference pulls you thin and squeezes you side to side. People call that spaghettification, and the name fits a little too well. Around supermassive holes, the gradient at the horizon is tiny. You could cross alive, only later facing stronger interior tides. Around smaller holes, the gradient kills you before the horizon. Here is the mechanism: gravity scales with 1 over radius squared. At fixed density, bigger mass pushes the danger line outward slightly, but the horizon radius grows linearly with mass, so gradients drop. Now a real event: a star once strayed too close. Its near side tore free and wrapped into a glowing stream. Telescopes saw a flare equal to between 10 to the 44 and 10 to the 46 joules. That debris spiraled inward for months, feeding the core relentlessly. So the picture is clear: tides set the tone of entry. Step away from drama and look at the bookkeeping. A black hole has entropy proportional to the horizon area. That means more area equals more ways the microstates can arrange. You should care because this sets the ultimate storage capacity. Add energy, the area grows, and the entropy ticks upward. Spin can change area, but net growth wins when you feed it. Hawking radiation slowly leaks energy and shrinks the area instead. That process is glacial for big holes, far longer than galaxies. The puzzle once screamed that information might be lost forever inside. Modern thinking says the information escapes, encoded in subtle correlations. The outgoing radiation is not random, it is delicately structured. No one reads that structure yet, but unitarity likely survives. Example scale check: a solar mass hole stores absurdly many bits. Its entropy dwarfs any library or any human-made archive. Feed it a camera, the mass grows, and area records it. Wait long enough, that record trickles out in ghostly heat. Net result: what falls in gets scrambled, taxed, and later returned. Switch scenes to quiet deserts and twin laser corridors at dusk. Those corridors measure ripples of spacetime, called gravitational waves. The idea is simple: accelerating masses jiggle the fabric itself. Care because even those waves can fall into a black hole. Waves carry energy and angular momentum, which the horizon can absorb. The hole responds like a drumhead, ringing in dying overtones. Those overtones are quasi-normal modes, set only by mass and spin. Absorption damps the ringing and leaves a smoother, simpler exterior. Meanwhile, part of the wave escapes, racing across the universe. That escape is what LIGO and Virgo have recorded repeatedly. A typical collision radiates energy equal to several suns annihilated. The remnant mass is lighter than the sum by that amount. The rest energy went outward as waves and inward as heat. Example numbers: the first event shed about 3 solar masses of energy. Seconds later, the ringed-on fingerprint matched a spinning Care black hole. Bottom line, even gravity's own ripples can feed the hole. Here is a twist: the brightest things near holes never cross. Relativistic jets shoot outward from plasma outside the horizon entirely. Magnetic fields anchored in the disk twist and fling matter away. Rotation drags spacetime, creating an ergosphere outside the horizon itself. Inside that region, you cannot stand still relative to far stars. Clever trajectories there can drain rotational energy from the hole. That theft is the Penrose idea, updated by magnetized plasma physics. The Blandford-Zenagic mechanism channels spin power into colossal jets. Those jets light up radio lobes across tens of thousands light-years. Meanwhile, light can nearly orbit at the photon sphere outside. Miss the edge slightly, and you slingshot out after several loops. Miss inward slightly, and you spiral through, forever out of touch. What about the last safe track, that inner stable circular orbit? That is the disk's inner edge, feeding the core most efficiently. Example: Mate 7's jet is wider than our solar system near launch. Net result: not everything nearby falls, only the unlucky cross. So the surprising answer is broader than it first sounded. Matter falls, light falls, waves fall, and even space seems flowing. Outside, we only get mass, spin, and charge as a memory. The rest becomes heat, geometry, and faint whispers far in the future. Remember the opening claim about light vanishing? That was the easy part. The real twist is that energy itself is the admission ticket. Feed the horizon anything energetic, and the black hole grows. If this cleared the picture, I would love your company here. Subscribe for more clear, calm tour of a very weird universe. Thanks for watching and for bringing your curiosity through the dark.